In this video, I will derive the mathematical model of the double pendulum, one of the most famous examples of deterministic chaos. Before demonstrating the Python simulation, I will first show how the equations of motion are obtained using Lagrangian mechanics. This demonstration will allow us to understand why such a simple mechanical system can behave in such a complex and unpredictable way. We describe the double pendulum using two angles, θ1 and θ2. Both angles are measured from the vertical downward direction. The coordinates of the first mass are x1 equals L1 sine θ1, y1 equals negative L1 cosine θ1. The coordinates of the second mass are x2 equals L1 sine θ1 plus L2 sine θ2. y2 equals negative L1 cosine θ1 minus L2 cosine θ2. The potential energy is given by V equals m1 gy1 plus m2 gy2. After substitution, the expression becomes V equals negative parentheses m1 plus m2 parentheses times g L1 cosine θ1 minus m2 g L2 cosine θ2. Because the second mass moves with contributions from both angles, the kinetic energy contains nonlinear coupling terms. The full expression is T equals 1/2 parentheses m1 plus m2 parentheses L1 squared θ1 dot squared plus 1/2 m2L2 squared θ2 dot squared plus m2L1 L2 cosine parentheses θ1 minus θ2 parentheses θ1 dot times θ2 dot. The Lagrangian is defined as kinetic energy minus potential energy, script L equals T minus V. The equations of motion follow from the Euler-Lagrange equation. d by dt of partial script L with respect to θi dot minus partial script L with respect to θi equals 0. After simplifying, the two coupled second-order equations can be written compactly in matrix form. This matrix equation is usually written as A alpha equals B. Thus, alpha equals A inverse B. These two quantities, θ1 double dot and θ2 double dot, completely determine the dynamics of the system. To prepare for numerical integration, we define the angular velocities. Let ω1 equals θ1 dot, ω2 equals θ2 dot. The system becomes four first-order equations. θ1 dot equals ω1, θ2 dot equals ω2, ω1 dot equals θ1 double dot, and ω2 dot equals θ2 double dot. These four first-order equations are the exact system that we will integrate using the Runge-Kutta method in the simulation. After deriving the equations of motion using Lagrangian mechanics, the next step is to simulate the motion of the double pendulum numerically. In our project, we use the classical fourth-order Runge-Kutta method, commonly called RK4, to integrate the system over time. RK4 is one of the most widely used numerical methods for solving ordinary differential equations because it offers an excellent balance between simplicity, stability, and accuracy. Here is the basic idea behind RK4. At each time step, instead of estimating the motion using only the slope at a single point, RK4 computes four different slope estimates. K1, the slope at the beginning of the time interval, K2, the slope at the midpoint using K1 to predict the intermediate state, K3, another midpoint slope, but using K2, K4, the slope at the end of the interval, using K3 to predict the final state. These four slopes are then combined into a weighted average. This averaging process makes RK4 far more accurate than simpler methods like Euler's method, while still being easy to implement and computationally efficient. In practical terms, RK4 helps us capture the highly sensitive dynamics of the double pendulum without introducing large numerical errors or instabilities. Even though the system is chaotic, RK4 allows the simulation to faithfully follow the fast-changing motion over long periods of time. Now that we have derived the equations and explained the numerical method, let's take a look at the actual simulation results. On the left side of the screen, you can see the real-time animation of the double pendulum. The two rods, the masses, and the trajectories are all computed using the RK4 method we discussed. On the right side, we have the phase space portraits. The blue curve represents theta 1 versus omega 1, and the red curve represents theta 2 versus omega 2. These diagrams give us a deeper view of the underlying motion. Let me demonstrate how different parameters affect the system. First, let's look at one of the most famous properties of the double pendulum: sensitive dependence on initial conditions. I will start with both angles set to 90 degrees. Then, I will run the simulation a second time, but change the second angle by only a degree. Even though the initial states are almost identical, you will see that the trajectories stay close only for a short time. Eventually, the two motions diverge dramatically and follow completely different paths. This drastic separation from a tiny difference in initial angles is one of the signatures of chaotic motion. Next, let's explore the effect of damping. With zero damping, the motion remains chaotic and the phase space curves never close. They continue to wander around, forming complex shapes. Now, let me gradually increase the damping value. As soon as we introduce dissipation, the motion becomes smoother, and the phase space trajectories begin to shrink. Eventually, the system settles into a simple, predictable swing. This shows the transition from chaotic dynamics to stable motion when energy is gradually removed from the system. We can also modify the physical parameters. If I make the first rod longer and the second rod shorter, the second mass moves much more rapidly and produces large loops in the phase space diagram. If I increase the mass of the second bob, its influence on the first pendulum becomes stronger and the entire system behaves differently. These examples show how strongly the motion depends on the mechanical parameters. The double pendulum is highly nonlinear, so even simple changes can lead to drastically different behaviors. Through these demonstrations, we can clearly see why the double pendulum is considered a chaotic system. The animation, the parameter controls, and the phase space diagrams together help visualize how complex the motion becomes, even though the system is governed by simple physical laws.